This is the video intended to show you the solution to the 2017 test paper. We'll start off with question number 1, 3 marks. You have a golf ball of mass 0.23 kilogram placed on top of a plane incline at 10 degree. So the ball is there. It's then led to roll down. There is no friction nor air resistance acting on the ball during its movement. By using appropriate physics concept, determine the speed of the ball as it reaches the bottom of the plane. So one of the solutions that you can give to us is by looking at the energy. Okay, so let me move up, just scroll. In terms of energy, remember that the conservation of energy tells that the energy at the top equals to energy at the bottom. With this idea, what you need to work out is that first of all, you can set the ground here to be the reference level, whereby potential energy equals to 0. If that's the case, you can say that at the top there, you only possess potential energy and it must be equals to the kinetic energy at the bottom. The mass of this golf ball will not matter, and G value here, GH equals to half V squared. Alright, and then G is 9.8. The height here, you have to be careful, this is the height that we are talking about. And the height here, if you refer to a triangle, the hypotenuse is 0.75 and you have a 10 degree over of the inclined plane. So how do you find the height? This component here is opposite of the angle of 10, therefore it is equals to 0.75 sine of 10. Okay, and it will be equals to half V squared. What's the answer for the V? You can put in your calculator. Your V shall be equals to 1.60 ms minus 1. So this is a one solution that can give to us. Now I shall move on to question number 2. Question number 2 is here. Question reads, by banking the curve of a racetrack, it's possible for vehicles to turn in a horizontal circle without relying on friction. This is one important information. There is no friction involved. For a car of mass 1,500 kg, the angle bank is set at 11 degree above the horizontal. The curve has a radius of 165 meter and the car drives at a speed maintained its height. So number 1, draw the free body vector diagram for the car provided in the box. So you should draw it here in the box. But perhaps what you can do first of all is identify the forces. Number 1 force is due to the gravity. Secondly, you have a reaction force. We can call it as M. And if I want to transfer in the vector diagram, what I can do is that this is what I can draw. This is the vector of M. Alright, it's heading with a certain angle, and this is the direction of the gravity. And you will see these are the two forces acting on the car because there is no friction. And what we have here, this is a net force, namely the FC. Alright, so this is the answer. And if you analyze the questions carefully, this angle here shall be 11 degree. Okay, because if you refer back to this, 11 degree is here. Therefore, you translate to 11 on this side. Now let me proceed. How about the magnitude of the net force? How do I find FC? FC here you can find by using this right angle triangle. You do know that the W and FC making 90 degree. And perhaps I can use tangent. Tangent of 11 opposite over adjacent is FC over W. And FC is radially equals to W, tangent of 11, which will give me, the mass is 1,005, so 1,005 times 9.8. And don't forget that you have tangent 11, use your calculator, and you shall get 2.86 to the power of 3 Newton. Alright, so this is the answer. At closest approach, the 722 kg Voyager 2 probe flew past Neptune at altitude 29,240 km. What was the gravitational force acting on the probe at that moment? Neptune has a radius of 24,900 km, mass of 9.9 power 25 kg. For this, you can use the gravity formula, gmm over r squared. Alright, so now what I need to do is to plug in the value of the constant. First of all, the mass of the first object, Neptune, 9.99 to the power of 25, and the Neptune is 722 kilogram divided by the distance between both of them. Number one, you have to consider the radius of the Neptune, 24,900 km times 10 power 3 at the back. Please change to meter, otherwise you get it wrong. Plus the altitude here, another big number, 29,240 to the power 3. The whole thing here, you need to square it. And you should arrive at the answer here to be 1.64 to the power of 3 Newton. Okay, so that's how you solve it. The main problem here is that you have to realize you have kilometer to change to meter. Next will be calculate the acceleration due to gravity at the altitude above the Neptune. For this one, you can use the gravitational field strength formula, gm over r squared. Okay, and of course, substitute the capital G, substitute the mass of Neptune to the power of 25, and lastly, same thing, the R, you have to be extra careful. Don't forget, this is the radius of Neptune. You have to add up with the altitude at that moment, 29,240 km, put in meter, the R term here, square it, and you shall obtain 2.27 ms minus 2. So that's how you get this solution done. Okay, moving on. Going on to question 4. This question is requires certain explanation. And remember that you do not need to show any calculation. It will waste your time. So compare and explain the differences of these two trajectories, one on the Earth, one on the Moon. Being different here would be the gravitational acceleration. So first of all, what I can compare is that the maximum height will be different for both of them. To be more precise, please do mention that the Moon here, the maximum height is greater. Maximum height on the Moon is greater because the acceleration on the Moon here is lower. Please describe. 1 mark for the difference in the height, namely the Moon having greater maximum height, and another mark for the explanation because the gravitational acceleration is lower. And one more point that you have to tell us is range. Again, Moon here, the range here shall be greater. Okay, so one of the reasons that you can give is that because the time of flight for the Moon is greater. Somehow they are interrelated with the acceleration. Lower acceleration on Moon means the time of flight is greater, which in turn give you a greater range. So another 2 points here. So this is 2 points. Just now was 2 points. Last one tell us about the time of flight. Time of flight, the Moon again shall be greater because the acceleration on this on this object is lower. So you have to repeat this statement, which enables you to get another 2 points. So 3 different differences, and explain it briefly. Next, Tom has a mass of 55 kg and he sits 2 meters from the pivot on the seesaw, causing the whole system to be tilted And Michael, who weighs 450 Newton, and he intends to balance seesaw so that it's perfectly horizontal. Specifies clearly where he should sit in order to achieve his target. So perhaps number one you can do is that you have a pivot for a seesaw, and Tom is on one side, so this is perhaps Tom. So let me write down Tom, and you have one more guy over here, Mr. Michael. It's getting more and more difficult to write for unknown reason. So Tom here, if you look at the pivot, what we can conclude, Tom will produce a force and a torque. Same goes for Michael. And the direction of Tom here, if you realize the torque that is producing, it is counterclockwise. How strong is it? Depends on the R and the F. So Tom is sitting 2 meters from the pivot, so that's the R. The force shall be 55 kg times 9.8. Whereas for Michael, counterclockwise, what's his RF? You have to find what's the R, because R will be the lever arm, and the force for Michael will be 450 kg. You do not need to multiply by 9.8, and you then have to stick to the rotational equilibrium principle, namely summation of all the counterclockwise shall be equals to clockwise torque. And in this case, I have two formula. I shall equate these two. So I get 255 times 9.8 must be equals to R multiplied by 450, which in turn give me the R value to be exactly 2.40 meter from the pivot on other end. Okay, on the other end, so specified clearly, so be careful about this. So that's how you solve question number 5. And we shall move on to question number 6. Studies of the Sun shown that Sun is orbiting the center of Milky Way galaxy with orbital speed approximately 250 km per second. The center of Milky Way galaxy is located 30,000 light years from the Sun. Assuming the Sun is undergoing uniform circular motion around the center of Milky Way galaxy, calculate the Sun orbital period. So this is a uniform circular motion. We can apply V equals to 2 pi R over T. And what we are looking right now is the orbital period. It's 2 pi R over V. Okay, and the R here, be very careful. 30,000 light year. Change to SI unit, you have to multiply with the light year equivalent. 1 light year is 9.46 to the power 15 meter. That's the correct R value. And the speed here, be careful with the unit, is 250 kilometer per second. So 250 times 10 power 3, because you have to change the meter. The per second is fine. And time that you have is 7.13 to the power of 15 seconds. So that would be the answer. And move on is that, hence or otherwise, calculate the mass of the center of Milky Way galaxy. Alright, so hence or otherwise. So for this question, what you can do is that you can make use of the Kepler's third law. This is Kepler's third law. T squared over R cubed is equals to 4 pi square over gm, and m here referring to the larger object. Of course, comparing center of Milky Way galaxy with the Sun, this capital M shall be referring to the mass of the center of Milky Way galaxy, which is much heavier than the Sun, and we will inspect how much. If we rearrange the formula, the capital M is equals to 4 pi square R cubed divided by GT squared. And we shall do the substitution manually. The R value is 30,000 times 9.46 to the power 15. This whole expression, don't forget to cube it, and you have to divide by GT squared G is a constant. The period here you have find it out to be 7.13, about 15. Don't forget to square the entire expression, and you have this number here to be 2.66 to the power 41 kilogram. So this is one of the way that you can